Okay, so I'm going to experiment with using a screen recorder to solve the exercises. So the first exercise, use the Cantor-Lebesgue function to construct a continuous, strictly increasing function psi that maps the Cantor set onto a set of positive measure. Now the Cantor-Lebesgue function itself maps the Cantor set onto a set of positive measure. That's almost all of 0, 1, and it's certainly continuous, as you should have proved by now. But it's not strictly increasing. It is constant on almost all of 0, 1. That's another thing you should have proven by now. So we want to make a strictly increasing function. It's actually very easy. All we want to do is take our function, the Cantor-Lebesgue function, we add x. That makes it strictly increasing. But we still want it to be a function that maps to 0, 1. So we divide by 2 here, and we call that our function psi. So that is problem number 1 solved. Next, show that there's a continuous strictly increasing function on 0, 1 that maps a set of positive measure onto a set of Lebesgue measures 0. Well, we've got our function, the psi function over here, which we know takes the Cantor set and sends it to a set of positive measure, because the measure of this is greater than 0. So we want our function to go the other direction. We want it to send a large set of positive measure to a set of measures 0. And all you have to do is just take phi inverse. It's still strictly increasing, because the inverse of a strictly increasing function is strictly increasing. And it is still continuous. Now, how do we know it's continuous? It's easy to see that, first of all, because it's a theorem in Rudin, but also it's a general topological theorem. That if you have a 1-to-1 continuous function that maps a compact set into a Hausdorff, compact space rather, into a Hausdorff space, then it is a homeomorphism and has a continuous inverse. So this is the function we're looking for, and this is actually very interesting because you think of continuous functions that are very smooth, but these functions can stretch your set so much that they can send large sets of positive measure to measure 0 and vice versa. Next, we want to show that Lipschitz functions send sets of measure 0 to sets of measure 0. This is actually pretty easy to prove. Now let's look at the definition. A function is Lipschitz when the following property holds, namely the difference between the image of y and the image of x is bounded by some constant multiplied by the distance between the points. This actually is going to bound the stretching, so to speak, how much our function can stretch the original set. So let's say we have a set E, and we send it via a function f to a set f of E. Now, I claim that the measure of E is 0. How can we show that the measure of f of E is 0? Well, since the measure of E is 0, I can find the following thing. I can find a collection of open sets, k equals 1 through infinity, ak, bk, that cover it, and that the summation of bk minus ak is less than any epsilon I like. Next, I'm going to take this collection and I'm going to observe that f of E, well, that just contained in the union from k equals 1 to infinity of f of ak f of bk. Well, how big are these intervals? Well, this is the length is f of bk, the sum of f of bk minus f of ak. But by our Lipschitz bound, that's just less than some constant times bk minus ak, which is less than, which is actually going to be less than that constant times epsilon. Since epsilon can be arbitrarily small, if I send epsilon to 0, I observe that the measure of f of E is still 0. So that's problem number 3 solved for you. And problem number 4. Well, the Cantor-Lebesgue function is not Lipschitz. Well, this is pretty obvious, because if the Cantor-Lebesgue function was Lipschitz, it would send sets of measure 0 to sets of measure 0. But it sets the Cantor set which has measure 0, and it sends that to a set with measure 1. So obviously the count-Lebesgue function is not Lipschitz. It's not even absolutely continuous, but I'll discuss that another time. Tell me what you think of these videos. Thank you.